Okay, now that we've seen that grow like that, now we're going to focus on the details to show that expansion, to draw some things in there and show some of the features that are important. We've seen it grow, and now we're going to take a look at a static situation so that we can point out some of the features. Looking at image 065, this just shows that there's nothing really special about those flat segments. Those once you've pulled off a string, pulled off threads off of that expanding or off of that center region, they can be a lot of different shapes. This just illustrates. One of them is circular, the one on the left, and the other one, that's a triangular organization. But so just to point out, we don't have to have that any particular configuration, but we in this work would generally pick the one that's just got the simplest math with it. As we look at slide 070, again with a reminder that we're not really, the purpose isn't teaching. With this video you should get the slides so you can take a look at them, but in the course we'll go into this in more detail. But as you look at this, the last part after it's grown fully, you see the black triangle there. That's called the expansion triangle. And what happens is that each iteration, that expansion triangle represents, you could think of it as first a void that is filled from within the strings that are inside the channel. So every time for every iteration, all of those strings shift up. It's as if the expansion triangle opens up and then the threads are filled in. So the little red marks in there show the radial expansion at each place there. You see the top radial expansion is C units. We use C because this is going to be the speed of light. And then each fractional point along there has expansion that's fractional expansion. So in this particular case, we've got the full and 3/4, half, and 1/4. So those four strings represent those fractions. So this is the nature of that expansion triangle. Is going to be very important. You notice that it has that c² property. And if you will remember energy, Einstein's kind of energy is equal to mc². So we're going to find that c² shows up in our analysis of the substance flowing into this web. It flows into that triangle, and the triangle has area that's proportional to c². So that expansion triangle is a really important thing. One of the potential confusing items or aspects of this work is that we do these demonstrations with this great circle so that we're just dealing with one dimension. It's very easy to demonstrate, but that material that we are sending out in that those tangential directions, that can be spun around and distributed. For instance, when we are dealing with the sphere, or like Sphereland kind of universe, then each one of those strings could be redistributed around in a circle. So, and it would get thinner, and it would have certain properties, but still, we can take this approach of dealing with a great circle, dealing with the material flows there, and on the tangential flows, we distribute them in every direction of the actual out there space. So this falls in line with the general idea that we've got in here, the in here spine of the atom, and out there is all the pointing directions that are possible. With a great circle, we just have, back and forth. And with then with Sphereland, you have a complete circular thing where you can point. And then with a universe like ours, it's a sphere. And so in any case, for each point in that expanding web, each point along the atom's spine, that little increment of material that goes out into the tangential area gets distributed throughout the space. So we're going to see some little diagrams about that. That's just illustrating that we're just dealing with this circle, but that does expand on up to the larger dimension cases. image 07575 just illustrates that. To the very left, you see the simple case of material going out in each direction, like we were doing with that first set of strings, and also with the web that had 4 pairs of tangential strings and 1 pair that stays vertical or radial. And then in the middle, you see that same thing fanned out in a like a disc. And on the right, it's harder to illustrate, but they could also be distributed throughout a space. So things get thinner, of course, but the neat thing is that when you get to the case on the right that would be like our universe, then it gets thinner in proportion, inversely proportional to the square of the distance, just like gravity. And that really comes in much later in this, because gravity does come into this work. It's a natural fit. Okay. Well, in this one, I seem to be doing a ridiculous amount of camera on stuff. But what we're going to switch to now is just to pointing out the fact that we can deal with